So, isotopes, and our last little jaunt before we push into in the periodic table organization. Our protons define which element we're looking at, and neutrons define the isotope. Or said another way, they define the mass number. Okay? Our mass number is the sum of protons and neutrons. And because that is a difficult thing to go through and identify, for some compounds, we go through and call them isotopes, if said isotopes exist. Right? So isotopes are the exact same element, they just weigh differently. They have a different mass. Right? So the example we could look at would be, say, hydrogen. We have hydrogen 1 and we have hydrogen 2. Right? And what those are referencing is, if we go through and look, the only thing that is different is the mass number written in the upper left-hand corner. And so if we look for hydrogen 1, this is hydrogen 1, and this one is hydrogen 2, we're saying their mass has changed. Well, how has it changed? Well, for hydrogen 1, how many neutrons do we have? Well, how did we say we solved for neutrons? We solved for neutrons by setting up our little math. 1 minus 1 is 0. For hydrogen 1, there are no neutrons. Right? There's 0 neutrons. For hydrogen 2, 2 minus 1, we have 1 neutron. Okay, so our little mathematical system helps us sort that out nicely. Okay? And that's really all an isotope is. For certain elements, there are super common isotopes, or isotopes that have been studied for a very long time. And so hydrogen, being the smallest element, has two very commonly studied isotopes. We have protium and we have deuterium. Well, in the case of protium, if we think about what it was made of, it didn't have a neutron. All it has is a proton. Since we're looking at the nuclear notation, just one proton, let's just call it protonium, which sounds kind of stupid. So we backtracked it a little bit and we get protium, which is really the origin of it. Right? It's just referencing that we have only a proton in that nucleus. What happens when we move to deuterium? Well, we can't call it pronudium because that just sounds, well, actually pronudium doesn't sound too bad to me. Okay, but we decided that doesn't work. Right? And so we look at our Greek language prefixes and we're saying that do, as in deuces, or going to drop, never mind, deuces, as in number 2. Okay, so what are we referencing there? Well, there's 2 particles in that nucleus, 1 proton, 1 neutron. So 2, we get deuterium. And we now have deuterium. That's it. Okay, so isotopes are just different because they have a different mass. This does bring up kind of a different notational change, because we can determine the protons and neutrons from the atomic notation. We can also write it out differently, because this kind of notation of writing number above number is difficult to type. We came up with a typed notation, and that's what we're referencing here. So really what we're saying is we have lead, which is Pb, right? And we have 206. Okay, well, we already addressed this kind of indirectly earlier. Because we know lead is the symbol Pb, we know the atomic number. We know the atomic number would be 82. And we know that because we've got the periodic table, and we can look up Pb on the periodic table, and following the keys of our found on our periodic table, we know that the atomic number is 82. So 82 gets written down here. So then what the heck's that 206? It's possible that it's the number of neutrons, okay, but unlikely. When we consider atomic or nuclear structure, it's roughly 1 proton, 1 neutron, 1 proton, 1 neutron. And if you move into 151, they might talk about the belt of stability, I think is what it's called. I think it's called the belt of stability. And if you're interested in nuclear radiation, you can look up that term. I'm talking about belt of stability. Okay. And really what that says is that the ratio between protons and neutrons is 1 to 1. And as long as we're that 1 to 1 ratio, we aren't radioactive. As soon as we fall out of that range, now radioactivity starts to come into play. Right? So 82 protons and 206 neutrons would be way outside of that 1-to-1 ratio, okay? Hugely outside. So possible, but not very likely. What makes more sense for that 206 to be is the mass number, and indeed, that's exactly how we use it, right? So we write out the name of the element because we're required to know name to symbol. We know the symbol. As soon as we know the symbol, we know the atomic number. Because we then specify the mass number after writing the name, we know the mass number also. And so we now have our nuclear notation, which would then mean we could go through and do our long division of mathematics, where we set this up 206 minus 82, there's a 4, 1, yeah, somebody's not so great at math. So let's try that again. 20 minus 8 would be 12. There we go. So 124 neutrons. And we now know the number of neutrons and the number of protons. Right? So that's the way to read that notation. The next thing I want to draw your attention to has to do with the periodic table. So instead of trying to throw a periodic table into this or say, look at the periodic table on my wall, let's take a look at our periodic table. And just a small little section of it. Let's take a look at the hydrogen symbol. And if we go through and reference this, we very clearly have our symbol. Okay? And in this particular one, there's our symbol. And then we have our atomic number written in the upper right-hand corner. And then we have our mass number written underneath. But wait a second. The mass number is the number of protons and neutrons. You can't have fractional protons and neutrons, which means that's not a mass number. Okay? And if you look at your periodic table, okay, and look for that number, you'll find that it is not said to be the mass number. It is typically written as the atomic mass or the atomic weight. Should say mass, but it's the atomic mass. How is the atomic mass different from the mass number? Well, the atomic mass takes into consideration that when we look at, in this case, hydrogen, not all hydrogens have only one mass. Some of them are deuterium and have twice the mass. Okay, so the atomic mass is an average. Okay, it's an average mass of all the isotopes. So in this case, since we know we have protium and deuterium, we could go through and solve for protium or for hydrogen and see what its mass number would be. And if we go through and set this up to do an average, we take the mass of protium, 1, plus the mass of deuterium, 2, and we divide it by the total number of particles, which was 2. In this case, we get 3 over 2, which is equal to 1.5, and that is very clearly not the number written on the periodic table. What the F? Isn't it just an average? What's going on? Right? It is an average. It's an average mass for all atoms of a particular isotope, or all atoms for a particular element. However, in the calculation that we just ran here, we assumed, and we know what happens when you assume, okay, we assumed that protium and deuterium made up an equal percentage. They were both 50% of the total population of hydrogen. Okay? And you might be like, well, I don't see where 50% is written into this calculation. And most people don't, okay? Because when we think about a simple average has just chosen to ignore where the calculation came from. So let's write that out again. We had 1 plus 2 over 2. So we're going to shift that around. This is 1 over 2 plus 2 over 2, right? Nothing fancy there. And now I'm going to shift it out a little bit more. I'm going to say this is 1 over 2 times 1, right? Plus, I want 1 over 2 again, right? But this is now 1 over 2 times 2, right? Well, what did that 1 represent? That 1 represented the mass number for protium. What did the 2 represent? Well, that 2 represented the mass number for deuterium. Well, then what do those 1/2 represent? Well, those 1/2 actually represent 50%. 50%. Let's walk through that real quickly. 50 per cent, root words, cent, century, 100 per 100. What is 50 over 100? Holy snap dogs, that is 1/2. Right? What we have factored in the simple average is an equal percentage. It doesn't matter how many times you go through it. You could do this with 3 different things. It's still factoring in that equal percentage, and instead of being 50%, it'll drop to 33% if we're doing 3 different things. Right? We have already subconsciously included the percent in each of our calculations. This is the percent of our blue thing. Right? This was the value of our blue thing, plus the percent of our orange thing times the value for our orange thing. And what this is now giving us is a weighted percent. And what you're probably looking at here is being like, well, dang, why did I never learn weighted percent? And we talk about simple percentages. Simple percentages were the easiest case. If we want to scale out to larger things, we have to understand where those calculations are coming from, and that's where this weighted percent is coming from. So when we look at atomic mass, it is our weighted average mass for all of the isotopes for an individual element. And when we go through and look at hydrogen, hydrogen is roughly 99% protein. Right? There's not a whole lot of space down there, but let's go ahead and throw that in purple. 99% of this is protium. The value was 1. Right? Well, if 99% is protium, that means 1% of it is deuterium. And if we go through and run this calculation, interestingly enough, we come up to 1.01, or darn close to it. Right? And that's where our atomic masses are coming from in this concept of weighted percentages. Right? This is a challenging concept to deal with, and that's why we have a couple more slides here on this topic that you can potentially look at. So remembering what percents mean, right? It's the quantity over the total possible for our sample, and then I almost always forget to do it, multiply by 100%. Right? This can be expressed as by mass or by volume. Deciding which one you want to do largely has to do with which phase you're looking at. If you're looking at mass, you're typically looking at solids. If you're looking at volume, you're typically looking at liquids or gases. Right? If you can't really tell because it's not clear, they're probably referencing by mass. Right? But that's what a percent is, the partial over the total. Right? The partial mass over the total possible options. Okay, so if we were to look at an example, and this is one I won't work out, but I'll leave you to kind of go through and solve this, and we'll see it in a little quiz question here in a second. We have an alloy of copper and tin. If our bronze contains 79.2 grams of copper and 10.8 grams of tin, what is the percent copper in the bronze? So I'd recommend you solve that question. Then you could also be asked the question, how much tin is in 100 grams of bronze? Right? And because that question's too easy, I'm going to make a second question pop up. It's going to be a little bit harder than that. Okay? So spend some time, work through those, make sure you understand the simple level of percentages before we move on to the full-on weighted average. And I do apologize because my picture is kind of floating in there. See if we can slide that around a little bit. Okay. A simple average assumes the same number of each object, or the same percentage of each object. A weighted average takes into account that we don't have equal amounts of each of those objects. Okay. So if we were to look at exams versus a reading assignment, right, we could go through and evaluate them as weighted averages if we wanted. that weightedness has already been factored in when we consider the number of points. When you look at the points for a reading assignment, admittedly I'm early in the sequence, but it's probably 2 to 10 points. And an exam is worth 100 points, right? I've already taken into a weighting by changing the point value of those. If we made them both 100 points, well, they aren't worth the same. We would weight the exam more because it's more important to make sure you know the content as opposed to you pretended to read the content. Let's be honest. Okay, so we have to kind of deal with that. So our weighted average is calculated by multiplying the percentage, okay, by the weight of the object as a decimal number and by its value. So there's a whole bunch of stuff going on in that. So if we look at the percentages that you need to work with, you have the percent of object A times the mass of object A plus the percent of object B times the mass of object B. Theoretically, we could do percent of C, mass of C, and this could be gone on indefinitely till we've covered all of our objects. When we added all of those things up, that would then equal our atomic mass if what we were looking at were the mass numbers. Right? Important things to acknowledge. The atomic mass is found on the periodic table. Right? The periodic table gives you this information, okay? And that's a common piece of information that people forget about. The periodic table has a lot of information there. Atomic mass is part of it. That's one I won't walk through in our diagram because every periodic table changes the exact locations of it. So make sure you look at the key for the periodic table, the legend that tells you where the atomic mass is. Okay? And it should say atomic mass or atomic weight. And that's found on the periodic table. The rest of this information has to kind of be given to you. Okay? So let's simplify this and let's go ahead and we're going to delete C because at least for the examples I give you, we'll only do two things. If I give you the percent of A and the mass of A, I'm probably going to ask you for the mass of B. Okay? And you might say, well, but shouldn't you be giving you the percent of B? And I'm going to say no. You need to figure that out too. This becomes questionable. How can you solve this equation if you have two unknowns? If there's only two things, and I tell you the percent of A is 50%, what is the percent of B? Why did you know it was also 50%? Well, we made the assumption that 100% is the maximum we could get. So if I take the percent of A plus the percent of B, it must equal 100%. There's the second equation that allows you to solve for the percent of B. Right? So we've got this big long expression that we can ask for any piece of given information within it. You have to recognize where the information can be stashed and stored because how it gets asked will change from exam to exam and from time to time. Okay, so with that, we'll go ahead and advance the slide once more. And by advance the slide, advance it to a question that I will give you some time to go through and solve. We'll see this pop up as an actual hard quiz question, and then the work will just appear. Ta-da! Magic. Almost, if I can figure out how to pause the video. I don't know if this is recording now, but dang technology. Technology didn't let me do what I wanted to do. So we'll have to walk through it a little bit more slowly. So here, you'll notice me underlining some colors to draw attention to different things. So if we start this off, we've got 60.11 per 100% times 68.926. We'll ignore units. This will probably be the only unit or the only section of the material where you're allowed to ignore units. Plus, we want the percent of 71. Dang, didn't tell me that. And then what I'm being asked to solve for is what is the mass? So there's that big old what giving us the question. There's our question mark, mass of 71. And then this would have to equal the atomic mass. And well, dang, I'm not given that either. So we've got a lot of big kind of questions that we would have to solve through here to be able to get through this question. So first and foremost, the atomic mass, that's found on the periodic table. And when I reference the periodic table, the mass for gallium is 69.72. So that number is going to need to go into that. Right? How do I get the percent of 71? Well, this is that tricky equation that I needed to remember. 100 equals the, whoops, do a different color. 100 equals 60.11 plus the percent of the 71, which means to solve this, the percent of 71 is equal to 100 minus 60.11. I could now sub that in, which then means what I'd be left with is just to solve for the mass of 71, which now puts me in an awkward spot because I don't have a calculator and I don't have an easy way of doing any of the math behind this, except sort of longhand. Man, really? That just blows. Okay, so if we were stuck like this on an exam, you wouldn't, come to think of it, because you will always have a calculator within the exam system. That's got to be what, a 9, 8, 39, 39.89. So we could now sub that into this. We get 39.89 over 100. Our atomic mass, we said we could pull from the periodic table, 69.72. And now all we've got to do is do our math in the calculator. And man, I just goofed everything on this one. Our math in our calculator to go through and solve for the mass of 71. Right? Unfortunately, I don't have a calculator handy. Hopefully the future videos won't have the same issue, but theoretically you can run that algebra. If you do have a hard time with that algebra, that's okay. You need to contact me so that I can help you out with that. Right? And with that, that is the end of this. So hopefully that worked out okay.